Hello, and welcome to Let's Meet the Virologist, a podcast about the people behind today's virology headlines, people working to understand viruses and how they affect you. We are talking with virologists, students and postdocs that belong to the American Society for Virology, so that you can learn who they are and what they do. I am Larissa Thackeray, and I am hosting this podcast from America's Heartland in St. Louis, Missouri. On November 12, 2021, we talked with Nora Herzog, a graduate student in the Holt, Mohr, and Wilson labs at NYU Grossman School of Medicine. Nora is in the microbiology and cell biology training programs and is currently investigating how early herpes virus 1 infection alters the biophysical properties of the nucleus to impact diffusion.
All right, well, thanks for speaking with us today. Why don't you tell us a little bit about yourself?
Okay, so I'm Nora. I grew up in Anchorage, Alaska. I didn't have any science education in my elementary school. We had an engineer come and talk to us about physics during 7th grade. And that was my first exposure to science. I didn't really have a true science class until I was in high school. I didn't have a lot of opportunity to really explore science, but I was always very interested, and my parents always really encouraged me to think about things scientifically. We had this great book. I think it's kind of old, but it's still one of my favorite books, which is like The Way Things Work. And it's got like all these funny illustrations and cartoons about, like how levers and pulleys work and things like that. And I always just loved building things, like building with Legos and blocks and stuff like that growing up. But I hadn't ever really had a biology course or anything about like life sciences until I was in high school. And I was very lucky. I had a really incredible teacher my freshman year of high school, who was very funny and very relaxed and had absolutely no curriculum, I think. But he would just start talking and we would just be like chatting, and whatever our subject matter landed on, he'd be like, okay, that's what we're going to talk about today. So I remember we had like a very interesting discussion on opioids, because there was like a meme circulating around about everyone trying to steal Oxycontin, which isn't that funny, of course, now that, we're like past really understanding the opioid epidemic. But we had like a lot of really, really intense conversations about biology and all these different contexts. And I just became really fascinated with it. I wanted to be a nurse, but that didn't happen, obviously.
Right. And I guess then how did you, when going into undergrad, what did you study? And then how did you get into your sort of PhD?
So I actually applied to nursing school during my undergrad, for my undergrad, and I was accepted into nursing school. And I spent one semester at the nursing school at UW-Madison, University of Wisconsin-Madison. And I did not like it. I did not enjoy the subject matter. I wasn't feeling challenged, and I couldn't really see myself being a nurse. And I think that a big part of this, though, was that I had been accepted into this program for underrepresented minorities in science. I'm a first generation college student, and my family is also low income. So I was accepted to this program that introduced people like me to science and the different science careers. And as part of that, they paired us with a research person. And so I started doing virology research with Dr. Bill Sugden at the University of Wisconsin, and it changed my life. I just couldn't, I couldn't imagine not wanting to do something like that. It took me a little bit to figure out exactly what I did want, because I was very confused as to what higher education really was. I think I didn't really understand research, what it meant to do research. The thing that was probably most surprising was finding out that a PhD is not, in fact, a teaching degree. I thought it was a teaching degree for college, and I thought that until I had a conversation with Dr. Sugden about how I was like, oh, I just don't want to take the MCAT. Why would I have to take the MCAT to do research? And he was like, well, why would you be taking the MCAT? And I was like, because I have to be a doctor. And he was like, I'm not a doctor, not that kind of doctor. You can do a PhD, and it's a research degree. And that was kind of when everything started to click, that it was like possible to just do this, that I didn't have to, deal with people and people problems and medicine and cures, but I could actually just study how disease works. And that was like the big light bulb moment for me.
Yeah. So can you talk a little bit more about that? So, I think people sometimes, like you were saying, not being aware that research is even a profession.
I mean, I think a huge part of this is outreach, and specifically outreach with high schoolers. I think there's a lot of high schoolers who are going into college. I think especially from backgrounds like mine. I've noticed like a similarity in some ways between my experience and the experience of a lot of a lot of my friends who are immigrants, that their parents like understand what a medical doctor is, and they understand that that is success. And that is something that is, profitable and difficult, but like, that's kind of like the ultimate accomplishment. And I think even just having those conversations at career days, or even in the science classroom, about like, if you like science, what can you do in science, and what do those different degrees mean? Because I definitely, I didn't really get the full grasp of what any of this meant until very, very recently. I would say some of the stuff that I didn't even know was possible until I was already in my PhD program. But even just like introducing like, oh, with bachelor's of science, you can work as a lab technician, and like, this is what that looks like. This is the kind of things that you can do. Or, you can work as a field manager for a project, or you can, do all these different things that don't necessarily involve like having to be a doctor. And I think also separating the difference between what it means to be a medical doctor and what it means to be a research doctor, and the ways that these two things are that like can sometimes be the same with like MD, PhD programs and stuff like that. But I think really having that outreach in high school is probably the most valuable thing, because I think that's when a lot of us get instilled like what does it mean to be successful? What does my path have to look like from here forward? Like, there's an immense amount of pressure on high school juniors and seniors to figure out what they want to do with their lives. And to some degree, you can get away from that a little bit in college and explore, but also because so much of STEM is so time intensive, there's this sense that you have to be doing it one way as soon as you get into college. And to just have that understanding that it doesn't have to be like that, and that there is this fluidity in what you can do and what you don't have to do. I think having that as young as possible is really, really valuable. And so I've actually become involved in several like high school and middle school outreach programs, like as a PhD student, trying to reach out to students who, like myself, didn't necessarily have the background from their family or large collection of people around them who knew what these things were and how this whole world of STEM works. So I think it's incredibly important to start that in high school, though. I think that's the key.
Yeah. And can you tell us a little bit then, like, how did you end up at your institution and in your PhD labs? Like, what were kind of some of the things you were looking for in sort of the institution, but also in the individual lab?
So as far as institutionally, I mean, I think I really wanted somewhere that would give me a lot of freedom, and not keep me boxed into one specific discipline. So I was applying primarily to schools that had umbrella programs, like programs where you're not like applying for immunology or for, microbiology or for neuroscience, but that you're applying to the program as a whole, and they have these disciplines underneath, but you don't have to choose right away. And I felt like that was really important because I've spent most of my life trying not to be pigeonholed into just one thing, because I think I have many diverse interests. And the idea of having to choose just one thing and just continue on that forever, I think was really claustrophobic to me. And I think that like part of this process of like learning more about STEM is also learning that like what you do in your undergrad doesn't have any bearing really on what you're doing in your PhD. You can go from, in my case, a cancer immunology lab and end up in a, molecular biophysics lab, which is kind of where I am now. And these are completely two different disciplines. I had no experience going into where I am now, and also knowing that, the techniques and strategies that I learn now are important, that's not necessarily going to have to be exactly what I do for my postdoc, which I would then carry into a faculty position if that's the track that I choose to go on. And I think that just knowing that as you move forward, you're not limited is also something that was really, really important to me. So I wanted a program that would really support me going forward without having to choose just one thing. And NYU is incredibly collaborative, very open departments. I'm currently co-mentored by 3 different PIs in 2 different departments. So I'm, half a microbiology student and half a cell biology student. And my labs kind of work at the intersection of like molecular virology and biophysics and cell biology. And transitioning to that, I made this decision because I felt like I was gaining the maximum opportunity to learn by entering labs where I had disciplines where I was completely unfamiliar with them. But at the same time, I've known ever since I was very young that I really wanted to do something with medicine, and specifically something with virology. As I'm sure many students have said, like reading Richard Preston's Hot Zone in like 7th grade, I was like, oh my God, this is crazy. This is so cool. And so like that was kind of my intro into science. But like I said, I didn't realize that I could do that without being a medical professional. So my intention at first was to become a nurse and be one of these people who works with either the WHO or MSF, in hot zone areas, like working on disease outbreak. And I think, going from that to realizing like what science actually looks like and what isn't possible, I never really lost track of, the lure of virology, though I definitely have absolutely zero desire to work with BSL-4 pathogens after realizing everything that it takes to, get up in those suits and how long it is, and, just the slow process of research under those conditions. I'd much rather stick with my BSL-2, and occasional BSL-3 pathogens than go into, those super high containment facilities. But all that being said, I knew that I wanted to do something with virology. And I think that, this was the first chance that I had to really, really delve into virology as a researcher. But it was also something that was very unfamiliar. And so I was looking to maximize my learning opportunity, and also to kind of prove to myself that, I can learn something in depth and new at this stage in my life. And like that is a process that I will have to be comfortable with, because for me, I think I would really like to see my future going into like the intersection of climate change and viral evolution and ecology, which is a different field than what I'm in now. And I think that just exercising that flexibility was really important to me, which is one of the reasons that I chose the labs that I did. And with the mentors that I have, who are incredibly, incredibly supportive of independent work, and have really let me craft my own proposals, my own methods, and really say like, this is why I think we should pursue this, with gentle nudges to like help me, steer back on track when what I'm saying doesn't make scientific sense. But they've been really, really supportive in terms of gathering a team to really help me become the best independent scientist that I can be. I think that's really valuable.
Yeah. And I actually feel like having co-mentors is becoming more of a thing in a way. So I've actually noticed that there's, at least at our institution, there's more students that actually have two people that are their mentors. So I haven't heard of three though. So you're, what's that like actually? Because it's hard enough to balance two co-mentors. So how does that work exactly?
So I do have a unique situation with three mentors. However, I'm not the only person at NYU who has this. And the other situations that I know where people have three mentors are similar to mine, where you have two mentors who kind of co-run their labs and they're collaborating with a third person. So my two virologists, mentors, they collaborate with each other. They co-run their labs. We have joint lab meetings. The research is shared. The mentorship is shared. I am just the only officially co-mentored student. And that had to do with the places where I saw my project going and whose research really was valuable in building like the path to that project. So I think that's why I have two additional virology mentors. But I really think that the collaboration between the two disciplines is super valuable because I get expertise from all different sides. And people see things in such different ways. It is hard because there are sometimes gaps where, some of my mentors may not know a specific thing. So if I don't know that there is a problem here, then it's very difficult for me to be like, oh, I don't know this and nobody else knows that this is a problem. So how do I get help with that? But I think having just like a lot of open communication between the four of us has been difficult sometimes just because there are four of us and that's, three very busy faculty member and myself as a graduate student. But the more that we like practice, I guess, coming together and actually talking about the research and different directions and different perspectives, the better that it gets and the easier that it gets. And also, I am going to say, as someone who really wanted very, very independent setting, I didn't want someone who was going to be hovering over my shoulder. I didn't want someone who was going to demand that I check in with them every week. And I know that's something that a lot of people really enjoy, especially having, like the structure of weekly meetings. So this isn't to say that that's a bad thing in the slightest. I just knew that that's not what I wanted. And I think that having multiple mentors who all have that kind of like hands-off, like let the student be independent approach, where sometimes I think if you just have one PI and that PI is a, kind of hands-off mentor, you can fall through the cracks pretty easily. But I think by having three, there's always someone there, always someone who I can check in with if I'm having a problem. And so I have not, like, I've actually heard from other people in my labs that they're having frustrations that I'm not, because I have other people who I can go to. And I think that in that way, the co-mentorship has been incredible because it's any deficit in one of my PIs is made up by the fact that I've got two others who maybe don't have those same issues. And so I feel like no matter where I'm turning, I still have a strong team. And of course, you can never expect any PI or any person to be perfect. So there's always going to be, small issues in communication or leadership style, anything where you might have conflicts, but having multiple people with even if they're like slightly different as opposed to majorly different styles in my case, is still really, really helpful.
Yeah. So let's come to it then. Why don't you tell us a little bit about your research and I guess sort of like what is sort of the thesis in a way, your main thesis, and then also maybe like what are the types of experiments that you're using to actually explore that thesis?
Okay, so I'm fairly early in my process. I only just qualified very recently. um, and so that's this is pretty new. But what I'm generally working on is macromolecular crowding in the nucleus in the context of herpes simplex virus 1 infection. So, what I study is basically how the biophysical properties, specifically diffusion in the nucleus at the 40 nanometer scale, changes during HSV1 infection, why that happens, and what is driving that change. So during HSV1 infection, we already know that there's massive remodeling of the nucleus. It's a DNA virus. It goes in, changes everything. But most of the remodeling that has been documented is happening in late stages in infection. And I have found that we are seeing massive changes in diffusion, like on the level of fourfold changes in diffusion at early time points before the onset of viral DNA replication and the expression of late genes, which is not something that has been shown before. And it's very exciting that we're seeing this change to this very fundamental property much earlier than we're seeing this remodeling that is well documented, that everybody knows happens. And so what I'm trying to do right now is to elucidate the mechanism behind that change. Now, a huge part of this is tracking diffusion, which traditionally is used. We traditionally would use microvirology techniques like microinjection, but that's very disruptive to the cell. So I'm actually working with a new technology, or fairly new technology, that was invented, I guess, by Liam Holt's lab, called GEMS, which are genetically encoded multimeric nanoparticles. And what they basically are is we use an archaea protein, an encapsulin protein from Pyrococcus furiosus, that self-assembles. We put it on a lentivirus connected to a fluorescent protein and a nuclear localization signal. We introduce it into the cell. The particles are synthesized, and then they self-assemble into these icosahedral particles in the nucleus, and they fluoresce quite brightly. And then what I do is I use tracking software. I take images, movies mostly, and then I put them through tracking software and analyze their movements mathematically. And that's how I get my measurements. But of course, this has quite a lot of different complications, including introducing the GEMs into different cell lines that are more favorable for virus infection, and just seeing about the different intersections between the effects of the GEMs and the effects of my treatments. So that's been mostly what I've been doing. Though, of course, I'm also working on protein expression. Of course, I'm using a lot of Western blots. I'm doing some RT-qPCR to check for RNA expression. But I think the vast majority of what I'm doing is imaging, because not only am I doing live cell imaging to track my GEMs, but I also use immunofluorescence staining to look at expression of different proteins under different conditions and their localization. Specifically, that's been very important, is looking at localization of GEMs in comparison to viral proteins. So a lot of what I do is imaging, but I do have some other more molecular techniques as well. And cloning.
Talk a little bit about, I guess, for HSV, when it's going to the nucleus, what does that actually look like? So what is sort of known about, maybe not so much about what you're starting to uncover, but just sort of like the canonical idea of what happens when HSV goes to the nucleus? So what are the early events? Is it like a single viral particle that goes there? Like,
yes, usually. Okay. So what we see is we see the I guess, like the engulfment of the capsid of the HSV1 capsid. traverses across the cytoplasm, and the genome is injected into the nucleus. And so during that process, you start to see as the genome, then this happens, like this is almost immediate. And so after the genome is in the nucleus, you start immediately with this onset of virus gene expression, which then shuts down host transcription, and just causes these massive changes again to the nucleus, both in terms of, so there has been quite a lot of literature on changes in host chromatin that are mediated by virus proteins, but you also see this major change in the RNA landscape as the shutdown of host transcription and the onset of viral transcription. So you just see like this incredible influx of new DNA and new RNA, along with the degradation and halting of synthesis of host. You also see shutdown of like the host immune response. So these are like classic things that happen when we see virus infection. But like I said, most of my work has really been focused on the biophysics of these changes, and how they might be influencing the cell from a biophysical standpoint.
Right. My question is sort of more, do you think that you're detecting changes now that basically were below the level of detection, or are you actually seeing them earlier in the life cycle than people have really looked? And if so, how early in the life cycle? Do you think it's response to the DNA itself, or do you require transcription?
Well, we've already discovered you need to have some base level of gene transcription.
Okay.
This is dependent on gene transcription. We're seeing it fairly early, like somewhere between 3 and 6 hours post-infection. With differences, it appears to be peaking at 9 hours. So you have definitely the onset. And again, this is independent of virus DNA replication. So this is mostly going to be with expression of immediate, early genes. And what we're working on now is trying to figure out when exactly temporally this is happening, and what genes are being expressed that are involved in this, and what genes then are sufficient to create this change. So that's what the experiments that I'm working on now are trying to elucidate. But what we do know for sure is that somewhere between the entry and the onset of virus gene expression and virus DNA replication, something is happening that is fundamentally changing the biophysical properties of the nucleus in regards to diffusion. And diffusion is often used as a proxy for molecular crowding. So they have an inverse relationship, of course. So an increase in diffusion would mean a decrease in crowding, which makes sense when you think about it, because if you have less space, things are going to move around a whole lot less. And so this is really, really interesting, because we do know that we see during HSV1 HSV1 infection, we do see an increase in acetylation of chromatin, which is creating a more open form of chromatin, which you would think might be causing an increase in crowding. But we're not seeing that. But again, the visible changes that have been documented with HSV1 infection, and especially with regards to chromatin, are happening at later stages in infection than what I'm looking at. And so really trying to elucidate exactly what is happening is very, very exciting.
Yeah. And I mean, I guess you're kind of early, but can you talk a little bit about, so what are your plans for the next sort of year or so? So, I mean, I think now, sort of some meetings are starting to be in person, so I guess maybe talk a little bit about, other than in the lab, what else do you do as sort of a graduate student?
So I've mentioned already that I'm very involved in outreach.
Mm-hmm.
I think this is something that's incredibly important. I know that I didn't have as much exposure to science as I really wish I would have when I was younger. Again, my parents definitely did their best, but as two people who didn't have college degrees and didn't really have access to a lot of scientific thinking themselves, this was mostly listening to NPR Science Friday and like reading the way things work, stuff like that. So I think that outreach is incredibly important, as I've already said. And so I'm very involved in that. I have monthly events that I orchestrate with a school down in the Lower East Side of New York that specially caters to underperforming students from backgrounds that are traditionally underrepresented in higher education. So I think this is a really good model, because rather than taking students who are high achieving, it's taking students who are struggling and then trying to give them the resources that they need to succeed. And we come in, a group of us from NYU, to teach them what scientists look like, and to start having like basic conversations on like how do you create an experiment? Like, how can we look at these different aspects of science in the world around us? We had a really excellent lesson on the physics of flight and aerodynamics. And we like just made paper airplanes with them, but we're talking about the different forces that go involved with airplanes. And, they have, I think at least they seem to be having a lot of fun, and it's a lot of fun. It's a lot of fun for me as well. And that's something that I care deeply about and have been involved with for the past couple of years. I'm also part of a mentorship program that pairs graduate students and postdocs with students in high school who are interested in STEM and who are from underrepresented backgrounds. And I am very involved in that as well. We have monthly academies where we have an in-depth discussion on one discipline in science. And I've been involved in creating the microbiology academies for the past 2 years, and just creating some resources for how do you write a college essay? What do college applications look for? How can you spin your resume, your CV to really reflect the things that you do, and stuff like that. So I spend a lot of my time doing outreach and mentorship. But of course, I also go to scientific conferences. I'm hoping that I can go to the Biophysics Society conference in February. I did apply, I haven't quite heard back yet. Hopefully I will soon, because they said early November. But I'm hoping I can go to the Biophysics Society conference. There's a really excellent herpes virus conference, the International Herpes Virus Workshop, that was held virtually last year that I attended, that was really excellent. I'm hoping I can go to that again this year and really get some specific feedback on the virus side of my project. I think having those two separate experiences is going to be really, really valuable. So I definitely try and attend around 2 conferences a year, just to, really expand my horizons. But my PIs are pretty adamant, of course, as is natural, that if you are going to a conference, you're going because you're presenting. So I'm hoping that I'll get to present at both, but we'll see. Keep my fingers crossed.
Great. And I guess just to finish up, sort of, do you have any idea of sort of the track that you want to follow later on? Are you interested in academics, or are you sort of seeing other or pursuing other paths? Where do you want to go from here?
I'm definitely interested in academics. I think I would really like to work at a university, probably not one like NYU, or at least not one like the hospital, but somewhere where there's undergrads. I think I've really enjoyed teaching and mentoring on an undergrad and early college level. And so that's something that I would really like to continue. I'm made very nervous by the fact that, we're graduating so many PhDs, and, there's not a whole lot of faculty positions open. So that's a little nervous making. But I think that's really where I would like to go. I mean, I'm fully a product of public education. And so I very much am an advocate for public education. And I had a really excellent university experience at public universities. So I think that, for me, I'd really like to be at a public university where I can, give back to the same environments that really help to produce me. But I have thought a little bit about more NGO fieldwork kind of research. There's some really interesting groups like EcoHealth and the Arctic Research Foundation that are doing really cool work with pathogens and climate change and, increasing prevalence of disease vectors and things like that. I think I could be happy in other places, but I think my number one goal is academia, which I know is maybe not the most popular answer at the moment. A lot of people are really enjoying the paycheck that they see when you can look at an industry job, and I do not blame them. But I don't think that I would be happy in that environment.
All right. Well, thanks so much for talking with us this morning. It was great talking to you, and good luck on your research. And we hope we hear from you in the summer for ASB.
This has been Let's Meet the Virologist, a podcast about people who study viruses. This is your host, Larissa Thackeray, and thanks for listening. You can find us on Google, Apple, Amazon Music, and other podcast providers, or at lmtv.podbean.com.